Itasca in 1985 after I did my PhD studies at the University of Minnesota. For about 15 years, I was general manager of Itasca's Chile office. So if you don't feel comfortable writing your questions in English and you'd rather write them in Spanish, I can take a crack at those as well at the end. I was CEO of Itasca International for 8 years, and currently I'm just a principal geotechnical consultant at Itasca, doing things that I really enjoy doing, and this being one of them. I've been an ARMA board member for about the last 6 years, and I've been helping for the last month or so develop this ARMA student design competition. So to tell you a little bit more about that, I want to introduce Juan Monsalve. He's a PhD candidate at Virginia Tech and one of 2 students who have been instrumental in pulling this competition together. Juan is vice president of the ARMA student chapter at Virginia Tech, and he's also part of the Itasca Education Partnership program. So Juan?
So thank you very much, Dr. Lorik. Welcome everyone. It is a pleasure to have you here. So today I'm gonna just give you some details, which I think if you have gone to our webpage, you already are familiar with some of them, about this ARMA student design competition. So first of all, I would like to acknowledge Dr. Lorik for all his help and support he has given Christian and I, while proposing this and working this to make it real. And Itasca Consulting Group, which is one of our main sponsors, along with the American Rock Mechanics Association and the College of Engineering of the University of Kentucky. So this idea was initially proposed by the student chapter of the University of Kentucky and along with our student chapter at Virginia Tech. So we hope you guys take advantage of this opportunity and make the best of it. So you can go to the next slide, please. So as the initial objective for this student design competition was to involve students from different universities that would offer rock engineering related programs with an engineering, real rock engineering problem. So we could test maybe their knowledge or also get them excited about rock engineering, which is a field I think most of us enjoy and like, and that's probably why we are all here. And the idea is that all the teams are going to provide the best solution that they come up with and then try to solve this problem. So with regards to the teams formation, I have been receiving a few questions from many people interested in the competition. So as we stated in the webpage and in the initial guidelines, the teams can be formed from 2 to 5 members. They could be both undergrad or graduate students, but we really encourage that your teams are formed by a mix of undergraduate and graduate students, and also, if possible, that you integrate maybe students from geology or geological engineering, civil engineering, mining, petroleum, or even environmental. It would be great to see teams conformed by multidisciplinary groups. So it is really encouraged from us. So each university is allowed to have more than 1 team participating. So that's not a problem if there's 2 teams from the same university. And another important thing is that the teams should have an academic advisor. This is mostly like to make sure that the people that is participating, that they are actually students. And 2 teams from the same university can have the same advisor. There's no problem with that. I just wanted to make that clear. And I think that would be all. So if you guys have any additional questions, just put those in the email. I'll be more than happy to answer those at the end. And this is just some important deadlines for you to take into account. The team registration period goes through April 16th, so there's 1 more week for your teams to be registered. If you want to register, just go to the webpage of the competition. in the registration tab, you just fill in that form, and I think by the end of Friday next week, when the registration period is over, we will be sending you all an email making sure that you are registered in the competition. Today is the webinar, and the competition will begin on April 19th. So on April 19th, we will be posting in our webpage all the details about the problem. We will also be giving you some guidelines on what you need to present in this initial document. So there will be two stages: an initial stage where you would submit a report. From that report, there will be like an initial selection where the judges will select a few finalist teams. So the notification will be on June 4th, and the teams will have like one additional week to prepare a presentation, which will be held online on June 11th, where they will be with the judges, and they'll be presenting their work for like a final selection. The results will be notified by June 11th, and the competition and the winners will be awarded during the ARMA annual meeting. So if you have any additional questions on this, you can go to the webpage for more details. And I just want to thank you all for being here today, and I hope you make the best of it. And thank you, Dr. Lerik, for your time and your interest in helping us with this. And I hope everybody enjoys this webinar. Thank you very much.
Thanks, Juan. So just a few more words on this. This is the first time that ARMA has developed a student design competition. So we're not exactly sure how it's all going to go. We think we have a good plan in place. But you know, be patient with everybody. I'm sure we'll refine this, improve it as the years go on. But I know as a member of the ARMA board, we're quite excited to be involved in this. And we think, you know, there's good value in these kinds of activities. I should say that the problem that we're going to present for you to solve is geared at, and it's a little bit hard to say because we haven't, you know, done this before, but we're hoping that it can be solved and written up and presented by working maybe, you know, a couple of weekends with your team, or, you know, certainly less than a week. You all are involved in your own studies and your own work, and this is something extra that we hope you'll get involved in and hopefully learn something from. And so we've tried to tailor the problem so that, you know, it's a few days worth of effort and maybe a little research and writing it all up. So the rest of the seminar, I'm going to talk about FLAC slope. I should say that you do not have to use FLAC slope to solve this problem at all. There are plenty of other tools available to you to use, and they are perfectly fine to be used in solving this problem. But we thought for anybody who didn't have access to other tools, this is one that you can use. It will allow you to solve the problem and work on it, and it's free. So that's why we thought we would at least go through this with you, and you can decide then what kind of tool you want to use to work on this. The FLAC slope problem is a special, or the FLAC slope program is a specialized version of FLAC for stability analysis. Now, FLAC is a very, very widely used tool, and it has lots of capabilities. It we won't be using all of those in this presentation. You can see some of the capabilities on the left-hand side there. But at the end of the day, it's a tool for solving slope stability problems in a very simple and straightforward manner. And hopefully you'll find that to be the case. And I'm hoping I can demonstrate that to you. It is, as I said, freeware downloadable from the Itasca website. The primary engine for this is a tool to calculate the factor of safety and slope stability. That's often the primary goal, is to find out how close to failure we are, and there are all sorts of acceptance criteria that are based on the factor of safety, typically on the order of 1.2, 1.3, 1.4, depending on consequences and risks and so on. But how does FLAC slope get to a factor of safety? Well, it performs a number of simulations with different trial properties to find the stability limit. That is the point where if we were to reduce or dial down the strengths any further, we would get slope failure. And so you can see the equations are quite simple down at the bottom, but the cohesion and friction or tangent of the friction are reduced by trial values to determine a safety factor. And this is often called in the literature a strength reduction factor. It's the factor that we have to reduce the initial properties by to see failure. So the question is, well, how good is this this particular trial and error scheme, if you like, in a numerical model? Well, we can compare it to some exact solutions that have been developed, and I'm showing you one here. We'll actually go through this, and hopefully we get a similar answer. We'll see. But this is a slope with a 45-degree angle. It's 10 meters high, and you can see the properties there in the lower right, 20 degrees friction and 12.38 kilopascals, a density of 2,000 kilograms per cubic meter. And so when we run that problem with FLAC slope, we get answers very close to 1. So the analytic solution that is compared to is based on what's called an associated flow rule. An associated flow rule is where the dilation is equal to the friction angle. And it's a special thing that allows analytic solutions to be found. Not that it's necessarily realistic. Most real geomaterial soils and rocks have dilations that are smaller than the friction angle. And the answers, and those are called non-associated results. So the dilation and the friction angle of the material are not associated with each other. But when we run this in FLAC slope, we get answers that are very close to 1. And you'll see that the answer differs slightly depending on the size of the grid that we use. And we'll talk about that as we go through here. You have the option in FLAC slope to select the sort of grid or the discretization that you want to use. And the answers will differ slightly based on that. As you get finer and finer grids, you get more and more accurate answers. But there's a point of diminishing returns. You don't need to make it so fine that it takes a long time to run. So what are the advantages of using a numerical model like FLAC slope to find the safety factor? Well, the first and primary one is that the failure mode develops naturally. It doesn't need to look for a trial surface in advance as limit equilibrium models do. But for simple problems, limit equilibrium and numerical models produce very similar answers. The difference starts to appear when we have more complex failure modes that limit equilibrium models are not able to resolve so well. And so that's where numerical models often have a particular advantage. But numerical models are not restricted in terms of their geometry, and this particular methodology of reducing the shear strength to find stability can be used in slopes, as we'll be looking at, also footings, tunnels, pillars, whatever you have. It's a very flexible methodology for determining safety factors. It doesn't involve any artificial parameters like inner slice force angles or so on. Everything in the modeling is very physical, and you can even stop things at intermediate stages, and they will look like physical, meaningful answers. We can develop multiple failure surfaces that have complex internal yielding, and very often this can happen in slopes where we have maybe a active passive mechanism forming. And we can also use structures in the models that represent rock bolts or geogrids or things like that. The example problem and the student problem that we're going to present does not require any of the structural elements to be used. Okay, well, so that all sounds good. What are the disadvantages? Well, really, there's only really one, and that's speed. Limit equilibrium programs typically run faster than numerical models. They usually solve in a number of seconds. Running numerical solutions with FLAC slope usually take, depending on the grid size, less than a minute up to several minutes. But there's no real drawback in using numerical models to solve these kinds of problems, given that we'll be able to solve these problems in a number of minutes, about the time it takes you to run and get a cup of coffee and come back. But there is one other perceived problem with numerical models, and that is that they are difficult to use. And FLAC itself is really no exception. It's a general purpose tool that solves all kinds of problems in underground excavations, slope stability, you name it, anything that is a geo-type structure, dams, tailings dams, can be solved with FLAC. But in order to make a particular class of problems easier to solve, that is slope problems, we developed FLAC slope, and it has a graphical interface that allows these models to be set up and run very, very quickly. So it should be, I hope you'll find, it's just as easy to use as a limit equilibrium program, and maybe in some sense a little bit more flexible. As I said, it does use the computational engine that is in FLAC, but everything else is kind of hidden from the user, and point and click operations are really all that are needed. So getting into a little bit more about FLAC slope, an analysis project with FLAC slope is divided into 4 stages, and we'll see how this works. The first stage is the construction of the model itself, and then the next stage is the building of the model, the boundary, the internal properties, the material assignments, and in our case we'll be considering the addition of water. But you can have all kinds of other things. You can have non-standard gravity to look at pseudostatic dynamic analysis for earthquakes, where you might want to have some sort of horizontal gravity component. You might want to have an interface to represent a specific fault or weakness in the geology. You might want to apply some loads that represent a surcharge. So all those things are taken care of in the build stage of the model. And then the final, or next to last stage is the solve. And part of that then is the selection of the grid, and then the calculation by the program of the factor of safety, and finally plotting of the results to look at the failure mode and so on. So these are the 4 stages that are used in FLAC slope analysis project. So the basic steps then within those stages, and we'll go through all of these, but just thought I'd list them up here on the slide so you have it. So the first thing is to develop the problem geometry, and there is a geometry which is called general, which is just as it says, it's general. You can put any sort of slope geometry you like together, and it will handle that. And then there is a build stage to define the geology, assign the properties to that geology, maybe put in a water table, and then select a grid and solve. Now, once you have that, you may want to change some things, and the design problem that we'll present to you will best be solved by then adjusting the boundary, because we're going to be looking to optimize the slope. And you may want to adjust the water to get better stability. And so you have all those things available to you, and I'll show you how that can be done, and you can keep on refining it as much as you like. So those are the basic steps that are involved. Just a couple of tips. One of the places where you may run into a problem is if you try to match the geologic boundary with a slope geometry that involves benches, and you try to match those things exactly. It doesn't happen often, but if you try to match them exactly, it may move the geology for you to a place you don't really want it to be. If that happens, just move those nodes slightly, and you'll be just fine. But it's always a good idea to try different meshing options, and I'll show you how that can be done. And start with a coarse mesh, and then gradually refine it. And so the mesh options are over there to the right. There's one that controls the density, and then the scheme, and there's all kinds of schemes that can be looked at, and it's just a matter of trying those and looking at how it appears to you and selecting one to go ahead with. So there is some help available. There's a help tab at the top, and this is what you'll see if you do that. If you click on PDF manuals, it says manuals. There's really only one manual. It's the FLAC slope manual, but it's very complete. It's over 100 pages. You can download it, you can print it, or you can look at it online, but it's very helpful. And so 2 of the problems I'm going to show you are, or at least one of them is in that manual with step-by-step instructions. So if you don't catch everything I cover today, you can go to that manual and read more about it, and I'm sure you'll be just fine. So the 2 problems that we're going to look at are shown here, and you don't need to write any of these things down. You can get a copy of this presentation after we finish, and you can have this if you want to try these on your own. But these are the 2 problems that we're going to start with, and then I'll do one more after that. So right now I'm going to finish the PowerPoint presentation, and I'm going to go to the FLAC slope. I have that pinned to my my screen. Oops. Oh, I'm on the wrong icon. It's the FLAC slope icon. So this is what you'll see when it comes up. And this is the start screen. Up in the upper left, you will see the 4 stages that I talked about: models, build, solve, and plot. And as you go on to each of those, you'll see what the various dialogues look like. But the first thing you have to do is select the model options, which is in the middle of the screen here. And it allows you to tell FLAC slope the kinds of things you're going to be doing. In this first problem, it's very simple. We're not going to be invoking any of these things. You also have the choice on the system of units. I particularly like SI units in terms of meters, kilograms, and second. That's pretty standard, but understanding that in the United States and some other countries, you might want to use English units, and you can do that, and all those units will come up for you in a consistent set of values. So what we do need to do then is start the model. We're not going to be using any of these options, and we could, if we had some previous projects, pick one of those. So you can go back to a previous project, but I'm just going to press OK, and it comes up with this dialog box. You can give the title up here, and I'm just going to say Chen because that's the analytic or the author of that analytic solution. And I'm going to give a file name, which can be the same or it can be different. I'm just going to call it Chen1, but it could be Fred or Bob or whatever. And it's going to go into this location where I'm doing all my work on this particular thing. And so it just says OK. So that's where all the information is going to be stored. And now I can build my model. So I have a new model I'm going to construct, and here are the options, the dialog box for the new option. And the easiest one is this simple model with just one slope. So I'm going to press OK on that. And so this box comes up, and you can see it here. Just 1 second. Sorry, my wife is book club in coming to look at things. So I had to move them to a different place. So this is the dialog box that construct the slope, and so the rise for this particular problem is 10 meters. This is the one that we were looking at with the Chen solution, and you just fill in these parameters here. So a 10-meter high slope with 45 degrees. The depth out in front here, I'm just going to make it 3 meters. And the left-hand boundary, I'll make 3 meters, and the right-hand boundary of 10 meters. And that's all. And so I can look at this now and see what that looks like, and that looks pretty good. So I can say OK, and I like that. Now these little handles up here with the little red boxes on the boundary, I could move if I wanted to, but I'm not going to do that right now. I've got this exactly where I want it. So I'm going to go OK, and I'm going to go to the build stage. And there's only one material here, so I don't have to worry about any layers. I'm just going to go to the materials, and then I'm going to create a new material. So if I look over here on the right, there's a button to create, and that pulls up a dialog box for the materials. Now, the class allows us to, if we wanted to build up a database of materials, and they would all be in there. So maybe you have something which is called fill or dump, and another one which is rock, whatever you might want to do. We don't have to deal with that now, and we don't even have to give it a special name. Just new one is good enough, but we could give it a name if we wanted to. Now, there are three different constitutive models available to us: a Moore-Coulomb model, a ubiquitous joint model, and a modified Hook-Brown model. And you're probably familiar with Moore-Coulomb and hopefully with Hook-Brown. A ubiquitous joint model is a Moore-Coulomb model that allows us, if we were to click on that, to define some joint properties in terms of their orientation and strength in a particular orientation. So it's very useful if we're solving problems that have very closely bedded geology, so schists or shales or things like that might be a ubiquitous joint model. But for this example, we just have a Moore-Coulomb model. The density for this model is 2,000 kilograms per cubic meter. The cohesion was this strange 12.38 kilopascals. Notice that the units are pascals here, so I have to put some zeros there sometimes. It's not kilopascals or megapascals, but pascals. The tension in this example was 0. The friction was 20 degrees, and that's all fine, so I'll put that there. I get a list of materials in the upper left, and there's only one. To assign that to this model, I just click on the area and any place inside the slope, and that will assign that material to this particular problem. So that's okay. And now we're moving to the solve stage, and I have to determine a grid. So I've clicked on solve. I have options for coarse, and that's what the coarse looks like. This is what the medium looks like, and here's the fine, and I could also do a special sorts of thing and look at different options for the mesh. For this example, it's fine just to use a coarse mesh. So there's the mesh, and all I have to do now to run this problem is solve for FOS. So I'm going to click on this icon for solve FOS. It comes up with some parameters to be included in the factor of safety calculation. In most cases, we're going to include all of those, but you don't have to. You could do what's called a partial safety factor for friction, one for cohesion. You could do all that, and then there's some tweaks to the bracketing algorithm, but you don't really have to worry about any of those things. So we're just going to run this as is, using friction and cohesion as the material that will be reduced. So here it's running up here, and it's doing this bracketing, and you can see the values over here on the right. It's running through here and honing in by bracketing on a solution, and it comes up and says the best estimate for the safety factor is 0.975. So that's the safety factor for this example, and we'd like to see what the failure mode looks like. In order to do that, we go to plot, and it shows the failure mode, and it's just exactly what we'd expect, almost a circular failure mode. It has these vectors that are showing the direction of movement. It has shear strain contours to show us where it's sort of localizing to form a failure. But up here on the upper left, we can see the project name, we can see the title, the model number, and then the contours over here. But most importantly, we can see the the factor of safety is 0.97. So we might want to look at some other things. So we can do that if we go to the items under plot, and we can see what some of the items are. We might want to turn off, for example, the fill of the strain rate contours, and we might want to look at plasticity indicators, for example. So I've just clicked that, and if I do that, then I can see this a little bit better. I can see, for example, where failure is occurring. I can see what the failure indicators are for the material. So most of them are these sort of reddish asterisk, which indicates it's at yield in shear, so it's a shear failure. But up at the top, we've got these little magenta circles indicating tension failure at the top. So this is, logical. We've got shear failure in most of the slope, but we have a tension failure. And if we did a little bit of a refinement on this, we could probably see a pretty nice tension crack forming at the top. So that's really all that I wanted to do with this example. You can see it gives a factor of safety very close to the analytic solution. So now what I'd like to do is go to the second problem that I had outlined as an example problem. So to do that, by the way, I could go up and probably should go to File and save this project, and now it's saved. I think it does it automatically, but just to be sure, you can save it. And let's go now to a new model. So I go back to the first stage, which is model. I go to new, and so I have a new model. This is going to be model 2. All right, let's call it something else. Let's call it tutorial. That's the name of this particular model. It's also going to just have a simple geometry like that, and we bring this thing up. But if you remember on the example I showed, the thing actually was facing the other way. So there's a simple way we can do that. We can make a mirror layout by checking this box at the bottom, and it'll flip it around for us. But now I'll just put in the values. The total height of that particular model was 14 meters. Sorry, the rise, I take that back. The rise was 10 meters. The slope was 2 to 1, so it had a run of 20 meters. So that's a 2 to 1 slope. The depth is this part in front of the toe, and we'll make that 4 meters. And the same for the left-hand part. The right, which is this part up here in at the crest, we'll make that one 15 meters, and we can leave the bottom where it is, the origin, and we can apply that, and now we have this kind of a slope, and that's fine. We like that, so we can press OK. And now this particular problem had 2 layers in it, so I'm going to go to build, and I'm going to define those layers. So this takes me to a different dialog box over here, and I'm going to add a layer to the model, and it happens to be at about 4.5 meters down from the top, or 9.5 meters up from the bottom. So if I just click anywhere inside of this model, it will put a layer there. You can see this red line then defines the division between these 2 materials. If I want to edit that and get it exact, I can press on this edit button, and I can edit this numerically down here at the bottom, and I can see well, it's not at 9.5, it's at 9.3563, but I can change that here and make it 9.5. And I can make this 9.5 as well, and that'll move that just a little bit, but it's exactly on 9.5 right now. So I'm going to press OK, and here's now my model with the two layers, but I have to assign some materials to this. So I'm going to go over to the material button, and I'm going to now assign materials. I'm going to create the first one, and well, let's call this the upper just call it upper. That's good enough. The density for this is 1500. And the cohesion is 5,000 kilopascals. So I put it's 5 kilopascals or 5,000 pascals. The friction angle for this is 20 degrees, and that's all that I have. So there's that particular model is upper, and I can put that there. And I'm going to create another model, a new model, another one we'll call lower, new material I should say. And it has a density of 1,800. And it has a cohesion of 10,000 pascals or 10 kilopascals. And a friction of 25 degrees. And that's okay. Now I can click anywhere in this lower part, and I have now two materials in here. All right, so I've got that, and this is okay, so I can go okay. And I can solve this. Again, you can see the different zoning options that are available to you. Again, we're just going to take the simplest one, the course model, and go to solve FOS, and we'll find out what the failure mode is for this. And we can plot this result. I'm going to go back, change the items, look at the shear strain rate for this. I'm going to take out the plasticity indicators, and you can see the failure mode for this particular setup with the factor of safety about 1.69. Now, if you'll recall, in the example I showed, it actually had water in it, and I can go ahead and add that in. Ideally, you do that at the beginning when you set it up. You click on the model option that includes water. I forgot it. I believe I can go back and get that now. So I'm going to go to File, and I'm going to look at Model Options up here, and I'm going to click on the one that says Water Table. So there's the water table now, and I'm going to go OK. I'm going to leave it as the same file name, and I'm going to overwrite what I had there. So now I've got this thing all set up. I can go back to Build, and now I have water out here. I can add in. I'm just going to move this water table to where I want it. And now this is just like the layers. I can move this around by just clicking on it, and you can see how easy it is to move this around and get whatever water table you like. So now we have water table in here. So I'm going to say OK. Now, one of the problems is that I forgot to talk about the wet density of the material. We only had a dry density. So I'm going to go back to the materials, and I'm going to edit those, the upper material, and I'm just going to edit that. Here's the material, and I had a wet density for that of 1800. I can either specify a porosity or a wet density. In this case, I'm using a wet density for that. And the same for the lower one now. I'm going to change its density by just assigning that here as 2100 kilograms per cubic meter. So now we have a different density above and below the water table, which is as it should be normally. So here's my problem now. Materials above and below the layer, and a water table, a slope geometry, everything that I need. I'm going to go to I don't need to go to that. Cancel or say, okay, I want to go to solve, go back to my course mesh and solve this. And here we go, it's doing the bracketing. Remember we had something, what was it, 1.67 or so before, and we're getting a lower safety factor now. That's what we would expect, 1.46. So we're going to look at the plot for this, and you can see it's a much lower, much larger failure volume. It goes much deeper into the slope, and we can see our safety factor up here. Now there are two model tabs down here at the bottom that would allow me to look at the previous results. Model 1 is this other example. The tutorial is this particular example. What I can do if I want to print out some information, and I'm not going to go in how to get hard copy plots of these failure modes and so on. I think you can figure that out with this print command and so on, or you can just clip and copy it that way. But I want to show you one other thing. If we go to File and we create a report, I can create a new report here. I'm going to call it just an HTML file, which is called report. You can give it whatever you want and say OK, and it's going to overwrite a previous one I have. But here is a summary of what I have done now in this particular example. It has the material properties, it has the safety factors, and so on. So that's a convenient way to get all of the information that you've used. So those are the two examples that are in the FLAC slope manual. I want to go now to the final example, which is going to be a lot closer to the student problem that we're going to give you. So I'm going to go to models and go to new, and I'm going to call this new model student. And I'm going to use a general geometry. So here we are, it's okay. Here's the geometry that I have to work with to start with. So the width I'm going to give as 1500, I'm going to give the height on the left-hand side 500, and the height on the right-hand side 1,000 meters, and that's it. So I'm going to apply that, and it looks like this. And I can say, okay. Now you can see that if I go on to this particular geometry, I can get handles on this upper surface, and so now I can kind of move this around to make it look more like maybe a slope stability problem that I might have some interest in. So I'm just going to do something like this, but that's all that's necessary. You just click and drag to the geometry you want. You, of course, could edit it numerically if I clicked on this, and I could change each of these points to some specific value. But for now, I'm just going to leave it as it is here. Actually, I'm going to cancel that. Whoa, yeah, I shouldn't have moved the other thing. So it always is good to show people your mistakes. So let's go back to new and start over on this with a general. Let me just grab that as 1,500, and the height is 1,000 or 500 on the left and 50,000 on the right. And I'm going to apply that now. Yeah, I should try not to grab the lateral boundaries. That's where I got in trouble, and that's why that got mixed up. So now I'll just go back and work on the slope part of it, not the boundary part of it. So let's just stick with that. Say okay. I'm going to go to build, and this particular example is going to have 3 layers. So I'm going to put in a layer at about 100 meters down. So right there is one. I'm going to have another one at, let's say 700 meters. So there's another layer. That's okay. So now I have 3 materials in this particular slope that I have to assign some properties to. So I'm going to go to material and create some new materials now. So I'm going to call this first one, let's call it soil. And it has a dry density of 2,500. It has a porosity of 0.02, 2% porosity. Notice when I do that, it automatically calculates for me. Oops, it's 2,500. It automatically calculates for me the wet density is 2,520. The cohesion here for this one is going to be 100 kilopascals. So I'm going to go here and put in 100 kilopascals. And a tension of 1/10 of that, or 10 kilopascals. Friction angle of 30 degrees. Dilation of 10 degrees. And that's that particular model. So that's the soil up here. I'm going to have a new material, which I'll call mid. And it's got the same density, porosity, but it has a higher cohesion has 750 kilopascals of cohesion, 75 kilopascals of tension. Friction in this example is going to be 45. Dilation is 10. And that's my second material. And so I'm going to assign that here. Notice I could assign other materials just by going on to this list and clicking on those and then assigning. That's not what I want here. I want a new material. So I'm going to create the last material, and we'll call this bottom, and put in the properties. Cohesion for this material is 500 kilopascals and 50 kilopascals tension. Friction of 40 degrees and a dilation of 10.
Excuse me, Lauren.
Yep.
I just wanted to make a note. One of those participants mentioned that one of the soil cohesions was entered as 1 megapascal.
Okay, I'll go back and check that.
Double check.
Good. Yeah, and I should say we're going to run a little over. Hopefully people can stay on. But we'll finish up pretty quickly here, and we'll still have time for questions. So don't worry about that. Let me get this one in here and then figure out which one I got wrong. So I'm going to go back to the first one and edit that. So that is supposed to be 100 kilopascals. So oops, did I get that right? Now you've got me. Yeah, so that should be right. Maybe the next one is down. Edit. This is the second material. Okay, I think that's all right. Probably. Hopefully I've got these right. We'll see. If we get a really high safety factor, we'll know. Let's just try it. That's okay. Let's go to solve and put a coarse geometry. Now this doesn't look very good. You probably want to run it with a finer geometry, but let's just, for the sake of this, whoops, I believe I forgot the water. I did forget the water, so I want to put a water table in here. Let's make it look something like this. We can just grab it and move it around. Now I have the water table. There we go. Let's solve this using a coarse mesh and solve FOS. Let's see what happens. So it has a, let's see what the failure mode is. So there's the failure mode for that particular problem. So, you know, I guess that's not too bad. It's a safety factor of 2, which is probably too high. And as I said, the problem is going to involve optimization. So let's go back and look at how we could optimize this a little bit. So we go to build and we go to bound. We can now steepen up these slopes simply by moving these things over and make this slope a little bit steeper. Let's try that. And now this is kind of what we have. We could also maybe consider that the water is a little closer. Maybe the dewatering is not quite so good. Let's look at that, and we can solve this problem. Oh, we have a coarse mesh here, and let's solve that. Now we're getting a safety factor 1.72, which is still too high if I'm interested in having a safety factor around 1.3. But maybe I'll stop here. I think, you know, from here on out, it's just a matter of going to the geometry, which is in bound, and sort of optimizing that. Maybe we make this thing a little bit steeper, or even a little bit higher, and changing the water table, changing the slope. Those things are all just sensitivities and changes you can make to the model, and as we try and optimize this thing. So I think I'll leave it at that for now. And Dave, you can maybe, if there are some questions, I can take those now.
Okay, great. Thank you, Lauren. We do have some questions.
Okay.
So the first one is related to the competition. Is it possible for team members to be from different universities or different countries?
Huh. That's interesting. We hadn't thought about that. I don't particularly see why not. I don't know, Juan, are you on the line? What do you think?
Hello, Lori. Yeah, I actually, we have been responding that answer, and we think that it would be easier just to have the students being from the same university, mostly because of the price and all this.
Yeah.
I think it would make things easier for the judges and everything. So we have been answering that it is the best to have just the teams from the same universities, I guess.
Yeah. 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 So, you know, here's something interesting. As I said, we're feeling our way through this. You know, maybe, and it's up to, probably Juan, to you and Christian, if you want to, they could form teams, you know, on their own to, you know, combine. I'm sure they have friends in other universities and other countries and so on. As a team, put the thing together and submit it, but not be eligible for a prize. Just as a, you know, something to do cooperatively and maybe learn cooperatively. You know, I'm just thinking off the top of my head that might be a nice thing for some people to do, but they wouldn't be considered in terms of any prize that might be awarded.
Okay, we can consider that. Maybe that they can send the responses, just but not participate for the prize.
Yeah, and you know, maybe the judges could look at their submittal and, you know, at least provide some feedback to them. But yeah, I see your point, and I think that's correct. I think we need to probably be fairly strict on the formation of teams in terms of assigning prizes, and limit those to one school. Yeah.
Mm-hmm. Okay.
Okay. How robust is FLAC slope when performing the shear strength reduction for materials whose strength is not defined by a simple cohesion and friction angle, for example, a nonlinear material?
Right. So if I go to build and I look at the materials that are available to me, and if I create, so the only one that would be nonlinear is a modified Hook-Brown material. I assume what they mean is a material which has a confining stress dependence, that the failure envelope depends on the confining stress. So a modified Hook-Brown model would give you that kind of behavior, but it's not set up to handle things like strain softening or any of the other more advanced kind of constitutive relations.
Okay. Is it possible to use the inherent anisotropy with ubiquitous model?
Right, that's really how its ubiquitous joint model is set up to introduce anisotropy into a model. So you can see the parameters for this ubiquitous joint down here. It really is a directional plasticity model, if you like. So the strength in all of the directions are governed by a more Coulomb strength, but in one particular direction, in the direction of the ubiquitous joints or the direction of the anisotropy, we usually have a lower strength in that particular orientation. So as I said, it's good for materials which have a very pronounced bedding schistosity, that kind of geology.
Okay. What is the interpretation of the velocity vectors? How do they help identify the failure mechanism?
Okay, yeah, good question. Let's just go back and look at that just a second. So these are the velocity vectors, and they are fictitious. In fact, you don't even, I guess you don't even see a scale. Oh, there's the maximum value of 1.77. But they don't mean anything in terms, it's not 1.77 meters per second. They really are just telling you about the failure mode, the direction of movement. If we get failure, how are things moving? And the reason they're not real is because this is a quasi-static solution that has damping applied to achieve a quasi-static solution. So while the directions of movement are real, their magnitudes are not meaningful, other than trying to identify the failure mode. Hope that helps.
What are the meaning of the shear strain rate, and velocity vectors again, in the result plots given the absence of shear modulus, bulk modulus, and other input properties?
Okay, so the good question. As I said, what FLAC slope does is it simplifies things. So it actually uses a bulk modulus and a shear modulus in the calculation. There's one there. You just can't see what it is, but it's there. The meaning of this is of the shear strain is very similar to the velocity vectors, just to identify where movement is occurring, and they are rates. So because they are rates, they're really not meaningful. While we're talking here, I'm going to make a little bit finer grid, and you can see maybe a little bit. When you go to a very fine grid, I don't know if this will do it or not, but you'll begin to get localization of those shear strain rate contours, and you'll actually be able to see better what the failure surface is. For the purposes of this demonstration, I used a very coarse mesh, so you don't see it quite so well. But here's one with a little bit better mesh. So let's look at what that tells us. So I should point out this is the previous result, and where my cursor is with the coarse mesh. Over here is the result with the finer mesh, and you can start to see now the concentration of the shear strains on the failure surface. You can also see a pretty nice vertical tension crack forming in the back here. So they're just all tools to look at failure modes that are being presented. And identifying failure modes is a big thing, and I think people don't pay attention to that enough. It really is important that you look at the failure mode, make sure it makes sense, and try and interpret it as best you can with maybe field experience or field evidence. But in this particular case, in a lot of these things where we have continuum models, it's shearing through the toe of the slope with a nice sort of formation of a tension crack in the back.
Next question. Tweaks were mentioned about the bracketing values in the FOS calculation.
Yeah.
Can you expand on that?
I've never done that, so I'll show you what that is. So those are here under the bracketing, and you saw how it goes about the bracketing. It actually takes a value in between the two values that it's looking at, and then decides whether it should be less than or more than that mid value. To be honest, you would have to go in and play with some of these values just to see how well it works. The idea would be to somehow optimize that bracketing scheme, and probably this is a holdover from when computers were a little bit slower. FLAC was developed in 1985, I believe, so it's 25, 26 years old. Computers have gotten much faster, and we've changed some things, but some things are legacy. I think this option to tweak the bracketing probably is a legacy from when computers were slower, but it's there if people want to play with it. You probably can read about it in the manual, the FLAC slope manual. I've never touched it, so I'm perfectly happy to wait a minute or two to get an answer. I don't want to spend my time trying to tweak it to get an answer in a minute 30 seconds instead of a minute 45 seconds. But it's there. You can read about it, and if you feel like it, you can change it. But I don't think it's necessary.
The next question is it's possible to compare the FLAC slope results with slide software, but I don't think we have anything like that.
Yeah, and there are, believe me, there are N numbers of papers, journal papers, where people have done that because that's what people are interested in. They want to know how good a numerical model is compared to a limit equilibrium model. And as I said, if you have simple failure surfaces like like we're showing here, the numerical model and the limit equilibrium models are going to be very close. The difference starts to appear when you have different failure modes, sliding on very weak surfaces. If you form a passive active block, if you have internal deformation, and that's because that's one of the problems with limit equilibrium is there's no internal deformation. It assumes that the whole body moves as a rigid body in many cases, so you can't get internal deformation. And people get fooled too. They look at the anisotropy and limit equilibrium, and they put it in, and they think that it's actually using that. But the anisotropy and the limit equilibrium model is only used if the failure surface runs parallel to that. So if you had for example, a toppling problem, you'd put in anisotropy, but the limit equilibrium model will never see it. It won't use it. So you think you're doing something that you're not. The numerical models, if you put in, a toppling orientation in a ubiquitous joint model here, it will use that to as part of the solution, because the continuum models, finite element, finite difference, whatever, each of the zones has its own behavior and its own properties and so on. And it's only when you put that all together into a large slope that you see what the emergent slope behavior is. So, if whoever wrote the question wants to write to you or write to me, we can probably provide, any number of comparisons. It's just as easy to go on the internet and find those papers as it is for us to provide them. But there must be 20, 30 papers of high quality that would allow you to look at that.
All right. Next question. What is the role of the water table?
Good. Yeah, I'm sorry, I didn't go through that. The role of the water table is to provide water pressure, and let me see if I can show you that here. So let's go plot items. Let's turn off the contouring. Let's put the pore pressure there, and let's put the water table on here and look at this. Okay, so here is that water table that we defined, this upper sort of magenta line, and you can see the pore pressure contours below. So it does two things. The main thing it does is it provides effective stress in the constitutive relation computation. So all well-formulated material models or constitutive relations work on effective stresses, not total stresses. And the pressures that are shown here are used in each and every one of those zones to calculate the effective stress and to see where it falls relative to the failure envelope. That's the main thing that it does. The other thing that it does, as I said, it provides a division between dry density of the material up above and the wet density of the material below. Now, in this particular case, and in most rock cases, the differences are small because the porosities are small. But the main thing that the water table does is to provide water pressure for effective stress calculations in the material model.
Okay. There is a second part to that question regarding the competition. For ARMA student design, what else are the judges expecting to see besides the basic software operation experience?
Yeah, so you'll see in the example, and I'll just tell you a little bit more about it. There is an economic part to it because it's going to be a open pit mining example, and you're going to be asked to sort of optimize the slope design on an economic basis. So that's part of it. The materials are going to have some variability to them, so the answer will ask you, to discuss how you handle variability, how you handle the economics, and what some other kinds of general things about what do you see in terms of risk if this was a real problem. So it's the backbone of it is a slope stability evaluation using some kind of software. As I said, it doesn't have to be FLAC slope, and then an optimization that. We're hoping everybody can manipulate programs pretty well and get answers, but it's a little bit about the thought process of going from the beginning of the problem through to the final answer.
Great.
But all those things will be detailed in the problem when it's set out.
Okay. The next question is just asking about examples using support, and I'll just add that there are several examples in the manual that you can refer to, and they include the data files, and so we would refer you to the FLAC slope manual to learn more about using support systems.
Yeah. I think there's good examples just from memory. Let's see. I think I have. I don't have the manual there, but for I think rock bolts and I think GeoGrid. I don't know what else. Those are the main ones. But yeah, as you said, if you've never looked at an Itasca manual, they are detailed in excruciating amounts. They're very well written, and you will have no problem finding examples for that and following them to the end.
The next question is asking about technical support. I guess regarding the software itself, and in general, since we moved FLAC slope to be freeware, we don't actually provide ongoing technical support for free for FLAC slope. Things like if you think there's a bug or in the software, that's something we would definitely respond to and fix if you think you've identified something like that. I don't know, Lauren, if you want to add something specific to the competition.
Yeah, I think so. I'll be surprised if you run into any problems that really require support, but you never know. And I would say, if you get stuck on something's not working the way you think it is, or it should be. You can send it to me. I'll try and work with or find somebody that will help. I think during the time period of the competition. But one of the things that there is, if as I said, if you save the project and it has a PSL extension, and if you're having a problem, I think if you just send us that particular file, we should be able to maybe sort out what the issue is. But I'm hopeful that we don't have just a a huge amount of problems, and if people do get stuck, I'll try and help them with that, and just so they don't get to a point where they can't get an answer to the problem. I'm not going to tell people how to get the answer, but if you get stuck with some of the mechanics of the running of the model, I'll be glad to help.
Okay. So Lauren, we still have another 10 or 15 questions, and we're coming up to 12:30. Would you like to continue, or would you like to?
Let's keep going. Maybe I'll try and be a little bit more succinct in my answers.
Okay. So the next question is, what are the units of the shear strain rate?
So strain is dimensionless, and the strain rate is dimensionless. So it's dimensionless.
Okay. In this example, are you able to, I'm trying to think, this is at 12:09, so I think this was the second example. In this example, are you able to analyze the failure in the mid-top layer step slope?
Let's see here. Let's see if I can go back to these. I don't know. It's not allowing me to go back. Let me see if I can pull.
Is it because the plots are turned off?
Yeah,
And there's water in that example?
Yeah, well, it's way down. But let me see if I can go to File and which project was it? Which one was it? The second one?
I think it was the second one.
That's it. There. Yeah. So say the question again.
Sorry, I'm sorry. It must be the third one because it's referring to the mid-level.
Oh, and the question was?
Are you able to analyze the failure in the mid-top layer step slope?
Yeah. Let me get to that one. There's no dates on these files. Oh, I think it was student, wasn't it? Did they call it student?
I think you did.
What I called it. Competition here. This one, yeah. So the question is, can you resolve the safety factor in the middle slope? Is that it?
Yeah.
Yeah. So you can exclude anything you want to from the calculation. So you could exclude the upper and lower materials from that calculation and find out what the stability of that middle unit is by itself. Of course, the other way to do that would just be to go in and give those other materials artificially high values so that they don't fail. But I think there is some facility if you go to solve and look at this. You can. Oh, we didn't have it set up to the beginning. You can exclude, if you do that at the beginning when you set it up, certain regions from the calculation of safety factor. But it can be done, sure.
Great. Can you change the failure direction of the model? Which I'm thinking is maybe the orientation of the model with the mirror flip.
So the only, I can't change the failure direction is what it is. I can flip these models around as we showed with the, you know, if you want to make it a mirror image, you know, if it's for presentation purposes, if it's easier to have the slope, you know, pointing to the left instead of pointing to the right, that's the only thing that's available there. So I don't quite know exactly what the question is. But yeah, let's go ahead and maybe they'll re-ask that question.
Okay. Can you use the software for probability of failure?
So, good question. Directly, you know, it doesn't do a probability of failure calculation for you. However, there are several techniques that can be used that will allow you to, you have to run some more models, but they allow you to calculate probability of failure, and those things are things like response surface method, point estimate method. There's some other things. So you could use FLAC slope to run the cases which are the basis for those probability of failure calculations. But it won't do it. It won't do it. FLAC slope won't do it automatically for you, not the way slide or some other things do.
Sorry, I'm just reading the question. So does the program just take automatically the most critical failure?
Yeah, it finds the most critical failure. That's the whole objective of the analysis. Is the software and is looking to find the most critical failure surface. That is the one with the lowest safety factor. And that's its whole purpose is to do that. But it does find the critical failure mode.
Okay. Does the program allow us to consider seismic effects dynamics?
So it doesn't do a dynamic analysis where you would feed in an earthquake record, for example, into the base of the model. So if you were doing a tailings dam analysis or any other kind of seismic analysis, there's really two ways to do that. One is to feed in an earthquake history to the base of the model. So it's the timed history of accelerations, and you would feed that into the base of the model and see what happens. That's a dynamic analysis. What most people do is something which is simplified. It's called a pseudo-static analysis, where you give a horizontal acceleration to the gravity. So if I had done that, when we set the model up and I had model options, I could have a non-standard gravity checked there. And then when I went to look at that, where does that come in? I think under build, here's the gravity. And so I could assign a horizontal acceleration. I could either move that little, this little wheel here to give the acceleration, or I could change its direction. I could give its components. For example, the vertical could be 9.81, and if it was 0.1 g to let's say to the left, I could have minus 0.981. That would be 0.1 g acting out of the model. We'll just see what this does then. So I've assigned a 0.1 g horizontal acceleration outside. You can see it's dropped the failure mode a lot. It was at 1.2. It's at 1.05 now. So that's how you would in most cases apply a dynamic analysis using a program like FLAC. The same thing would be true in limit equilibrium. You would apply a horizontal acceleration. It's called pseudostatic dynamic analysis because it's not really a dynamic analysis. You're just kind of assuming that gravity is acting horizontally or a component of gravity is acting horizontally in a constant manner. It's a very approximate method, but people use it and it's fine.
Right, and then of course for a full dynamic analysis, you would use something like FLAC. Correct.
If anything more serious would require a dynamic analysis, and those are require something like FLAC, and you then have to worry very much about what the shear modulus is and how it might change with different frequency components, and what the dynamic behavior of the materials are. And you change the damping, you could no longer use damping for quasi-static analysis. You'd have to reduce the damping way down to do those kinds of analysis. But those are very specialized things that are done for critical things like tailings dams and civil dams and things like that would use that kind of analysis.
Okay. Is it possible to observe the water pressures within the slope? So I think we've seen that.
Yeah. Yeah. So yeah, that was this plot items thing where I looked at the water pressures, so we can see what they are. You know, unfortunately, you can't. You have to sort of interpret what they are from the contours. You just can't click on it and find out what the pressures are. But, you know, for example, I guess if I'm over here in this yellow, it's, I don't know, 2.5 megapascals of water pressure. Yeah, the density of water, by the way, is taken to be 1,000 kilograms per cubic meter.
And also, if using the ubiquitous model, can we simulate failure modes observed in rock slopes, e.g. plane sliding or toppling?
Yeah, you can. The toppling is a little tricky because the toppling usually involves joints which are spaced, you know, 5, 10 meters apart maybe, and you get toppling on those. Ubiquitous joint model assumes that there is no spacing between the joints, so it's very finely spaced, and so you can do it with some care. You can use a ubiquitous joint model to simulate a weak layer, but you might want to also consider then just an interface for that as well. And again, those examples are in the manual. I didn't show any of those today.
What is the criteria for better safety factor? For example, is smaller than 1 better?
Say, what's the question again?
What is the criteria for the better safety factor? And then there, so like
okay.
smaller than 1 is better.
Well, there's two things. One, they might be a typo. They might have been asking about batter instead of better. Batter is, you know, a bench inclination is often called a batter. The safety factor is, you know, either set by kind of experience or it's set by kind of risk tolerance that that people are willing to accept. And it's different for civil than it is for mining. In all cases, you want to have a safety factor more than 1. You know, and if it's a very critical civil structure, you might want a safety factor of 1.5. If you have a temporary mining slope, which doesn't have much impact if it fails, maybe you want 1.1. But, you know, those are the kinds of ranges that people normally talk about, and there are all kinds of things, again, written about design acceptance criteria, what should be used for the acceptability of a design.
Right. I wonder if that question is also prompted because you were rerunning that last example, trying to get a smaller safety factor.
Oh, yeah. I was just trying to get something. I think we started out with 2, which, you know, in a mining environment you would never want. You want, because it's not economical usually, you'd want to have something closer to 1.3. So I was just playing with that, but you never would want to come up with a design which is less than 1. Because you'd be, unless you wanted to design for failure, maybe.
Okay. Does the software only calculate circular fault surfaces, or does it have an option to calculate non-circular failure surfaces?
So yeah, these problems that I showed you, while they look like they're circular, they're not. And let me just show if I can get back to what I had here. Oops. Where did the other one go? I think I lost that. But they're not circular, and the software does not define a geometry whatsoever. These simple models look like they're circles, but they're not. They're just not. They might look like it, but they aren't. and so they will find the failure surface that again has the lowest safety factor. And only in very simple cases is it going to be circular. Even those are not. If you would get the geometry and put it on there, they're not circular.
If you see some of the other examples in the manual, you'll see other failure mechanisms.
Yeah.
The next question is if other software packages are freely available, and the answer to that is we just recently made FLAC float freeware, but our other software is still commercial and has a cost to it. They all do have demos though that you can download for free and try out. And the only limitation to the demos is the size of the model. So you can run small models, even in dynamic analysis, all the options are available. The only limit is the number of zones or the number of blocks, depending on the software that you can run. In the case of pseudostatic analysis, which is the correct way to introduce a KH and KV value?
So with that gravity that I showed you in the example here, let's see what I didn't change any of those things. Let me go back and look at the model options and just do this again. So this has non-standard gravity. Let's see, I'm kind of doing some things backwards here, but I think it'll, and maybe some of these questions get asked, but those KHs and KVs would go in here with those components down at the bottom. And then you can put in whatever you like.
Great. The question is whether water flow is calculated.
It does not calculate water flow. FLAC can calculate water flow. FLAC slope just uses a water table or phreatic surface, and it assumes that the pressure beneath that water table is hydrostatic. So it's an approximation, and it's better for a more highly permeable material than a lower permeability material. But it's, again, a very common assumption in slope stability to use a phreatic surface. But, to do a proper flow analysis, you need FLAC or FLAC 3D or, some other program like FEFlow or MindDW or ModFlow, a proper flow program. But FLAC will do it, but not FLAC slope.
Okay. There's a question about the competition in terms of format basic requirements and whether the design needs to be published. I assume that will all be on the website for the
Correct.
competition.
Correct.
And the next question is about it's a specific one, what the J-angle button does, and I think that's on the plot. And that essentially, if you have a ubiquitous joint model, it will plot for every zone the orientation of the angle that you specify.
Yeah, let's just see what that looks like here. Let's take this bottom one and edit it. Let's see if I can do that. Let's just put a joint angle of 30 degrees there. I don't know if it's not going to let me do it without putting in some values. Let's put a joint friction of 25 and no cohesion. We'll just run this now. It's likely to look ugly, but that's not the purpose. Is to, so I put in the ubiquitous joint angle. Let's just run this thing and see what happens. But I can demonstrate the plotting so you can see what it looks like. So yeah, now we got a safety factor less than 0.5. I thought it would be pretty ugly. Let's see what. Here's with the ubiquitous joint. So it's this. Yeah. So that's kind of the model. It looks ugly because we have a very coarse mesh in here and a very low safety factor, less than 0.5. But what I wanted to show then is we go back to plot and items. Here's the joint angle. So there you can see that's the joint angle that we put into the model. So you can see what it is and try and see what it's doing, but it's making no sense because it's just a kind of a ridiculous problem.
Okay. How is it that we can generate pore pressure in continuing modeling? Because physically it's not possible to do in discontinuum modeling.
Just read it again.
So I'll read it in full. Kindly explain how can we generate pore pressure in continuing modeling, because physically it is possible in discontinuum modeling.
Okay, so you can generate pore pressures in continuum models. You can't generate any pore pressures in FLAC slope. As I said, you just have a phreatic surface, and that's all you get. So you have pore pressures that are the result of the phreatic surface. And I'm assuming maybe this question has to do with FLAC. You can generate pressures in rock, or you can generate it in soil. And you know, the classic case in soil is where you load a footing in a saturated media, and then as that pressure dissipates, you get settlement of that footing over time. So consolidation occurs, but you can generate high pore pressures in soil or rock. It doesn't really depend on whether it's soil or rock. You can do it either way. Either you're compressing a joint or you're compressing a matrix, and they both can generate. They both can dissipate. But again, those kinds of problems are solved with either FLAC or UDEC or 3DEC or FLAC 3D, and they can generate and they can dissipate water pressures, but not FLAC slope.
Okay. What is the difference between the shear strength and unconfined compressive strength methods of factor of safety solution control for Hook-Brown? So when you're in the solution.
Oh, yeah. Okay. Yeah. So let's just go back and just look at that a little bit. Let's edit this. So if we were looking at Hook-Brown, you know, one of the input parameters to Hook-Brown is the unconfined compressive strength. So you can do the safety factor analysis when it comes to time to do that different ways. I mean, the most common way, and the one which is a direct analog to what we do in more Coulomb, is to reduce the friction and cohesion simultaneously. Well, when you have a Hoek-Brown material, you have lots of frictions and lots of cohesions. So what you're doing is in each zone where you know the confining stress, you know the tangent to the failure envelope, you know the friction, you know the cohesion, you're dropping those things according to the strength reduction factor. Another way to do it that some people like to do is they say, well, I don't really know about that, but I know about unconfined compressive strength. And so they just reduce the unconfined compressive strength to get failure rather than reducing the whole failure envelope. Now, reducing the unconfined compressive strength affects the failure envelope, but you're just working with one component of the failure envelope. That's the difference.
Okay, so as FLAC is a continuum model and not discrete, which constitutive model do you recommend for rock mass? And if we want to include joints, how could we do that?
So, so for rock masses, in general, continuum models don't simulate rock masses particularly well. Although, you know, a Hoek-Brown model gets us towards that. The problem with continuum models is they really treat everything like a soil. Even a Hoek-Brown model treats the rock mass as a soil, but it provides good engineering estimates that people can use. So I guess in our work, we kind of recognize that, but we recognize we can't put every joint into a model that we would like to. So we often put, you know, as many of those in as we can explicitly, and the rest of it we make a Hoek-Brown material. With FLAC slope, you're kind of forced to make a decision. You're either going to use Hoek-Brown or going to use a ubiquitous joint model, and maybe you know just want to try those two different things and see what the differences are. We currently have in the Itasca library of models a Hoek-Brown model which also has ubiquitous joint behavior in it. So it's a Hoek-Brown material with the ubiquitous joints, and that's a pretty powerful kind of model for rock masses, but it's still a continuum. And a lot of behaviors are not continuum behaviors. Particularly brittle failure material models are not. They're not continuum. They're not well handled by continuum. But you know, sometimes you just have to use what you have and you know make interpretations based on that, realizing it may not be the best thing in the arsenal. But yeah, so first prize would be some sort of discontinuum model for rock. Second prize would be some sort of discontinuum model with widely spaced joints and a Hoek-Brown material between them, or a ubiquitous joint model between them. And third prize would, you know, be just sort of a continuum model with a Hoek-Brown material.
All right. Next question, and there's about 6 left.
Okay.
So in mining activity, there is seismic waves from blasting and equipment movement. How can we input that parameter in calculating FOS?
Yeah, pretty difficult to do. You know, the only thing you could do would be to try to convert that to pseudostatic horizontal acceleration. Most people haven't been successful at that. And most people don't worry too much about certainly equipment movement. They do worry about blasts, and we do those kinds of analyses, but we use a dynamic model to do that. So, and we explicitly model the blast and the propagation of the wave to the points of interest, to a slope or whatever. But it takes it takes more than what you're able to do with FLAC slope. It's a much more detailed analysis involving the explosive, the layout, the timing, and the propagation of those waves in a dynamic model to address those questions.
Okay. And of course, if you wanted to represent the after effects of something like a blast, you could have different properties, say, along the surface skin of your pit or slope with sort of reduced or damaged properties. But it wouldn't actually be the seismic event, but it would be that reduction in properties due to, for example, production scale blasting.
Right.
Do the displacements we obtain from a safety analysis have some meaning?
No, they don't. I should say also, this is a small strain model, so we're not modeling large strain. I don't even think you can plot displacements. I'll be surprised if you can plot items. No, there's no displacement on there. So we're really plotting. The purpose of FLAC slope is to distinguish between stability and instability. Its job is not to calculate displacements. Again, any of the other software in the Itasca family can do that. This is a very limited kind of capability model aimed at understanding stability. But so you can't plot displacements, you can't see them, and if you want to see them, then you have to use some other software.
Okay. Would it be possible to input a DFN model in a rock slope in FLAC? I'm not sure if they meant FLAC slope.
You can't do it in FLAC slope. You can input DFNs into 3-deck, and I think into UDEC. You can in FLAC 3D too. The 3D codes have that capability. So FLAC 3D 3-deck can accept a DFN.
Yeah, and UDEC and PFC as well.
Okay. Yeah, I wasn't sure if they could. And we also are developing a code called Slope Model, which would use DFN, but it's a nodal-based type of next-generation software.
Okay. Okay, so there was a clarification to an earlier question. Is the software usable for all types of failure?
Okay, so no. For example, you couldn't use it, as we were talking about before, a case where you generated a pore pressure either by loading or maybe seismic shaking. So if you were trying to simulate a tailings dam where material compacts and generates pore pressures, so you couldn't get that failure mode. You can't get any kind of failure mode that involves block behavior. Now, having said that, you can get a simple, one block kind of failure mode by putting in an interface to slide on and having a tension cutoff in there. So you can get a block sliding mode of failure, but you know, you're not going to get wedge failures. You're not going to get block toppling. You know, so there. But all of the other, you know, more, you know, continuum type failure modes you should be able to get. One of the things I didn't mention is the capability to do axisymmetric analyses. You have to get that at the very beginning under model options, but you can do an axisymmetric model, which allows you to look at things like slope curvature. You know, if you had a pit which was, and all pits are curved, so but to more or less extent. But the analyses shown here are all two-dimensional plane strain. That is, they're infinite in extent. But you can look at axisymmetric models where the pit or the slope is assumed to be either a cone or an inverted cone or a normal cone. It can go either way. But so there, and that's a nice feature to be able to use to try to examine the impacts of slope curvature.
Okay. In command prompt mode, when we solve the model, we get different output values of strain and displacement compared to when we analyze outputs after solving at the FOS. So I don't know if they're using FLAC.
Yeah, I think this is a FLAC question where you can get displacements and you can get much more information. Yeah.
And I think it's also the difference between when you're doing the FOS analysis, the properties are being adjusted to get to that failure, whereas when you're just running FLAC directly, or you're actually inputting a specific set of properties or properties with some distribution, but it's one case. So that might also account for any differences that you're seeing in results.
Yep.
Okay, a few more. Does the acceleration in the x direction, is that equivalent to the seismic coefficient for a limit equilibrium times the PGA?
Yeah, I think it is.
And
things like 0.1 G would be common for a horizontal acceleration.
Okay. Last couple of questions. Somebody's asking about the trench stability analysis for slurry used to model or diaphragm wall construction. So I would actually direct you, if you're interested in more trenching diaphragm wall construction, to look at FLAC, and there are a number of kind of civil wall construction examples in the manual, so and on the website. So I would direct you there. And again, someone's asking about support measures, and in either FLAC slope or FLAC, there are quite a number of examples that I would refer you to. And that is the end of the questions. So I'd like to thank you, Lauren and Juan, and thank everybody who attended. And for those of you who have stuck out to the very end, that's great. It's a fantastic response. So we hope this is helpful to people who are interested in the competition, or for others who are just interested in FLAC slope. And the presentation and the Q&A session has been recorded, so we will send an email out to everybody with instructions next week how to download the recording, the slides as a PDF, and and some other information. Thank you very much for your attention. This concludes the webinar, and I hope everybody has a good day.
Thank you.